You're listening to Scientific Giants Who Changed the World. Each episode stands beside one mind and follows a thread of curiosity until it ties to the world we inhabit. Today, we meet a scientist who treated invisible structure as a moral problem. He believed that if you understand how matter holds together, you also inherit a responsibility for what that knowledge becomes. His name is Linus Pauling, and his life is a rare hinge between chemistry's most intimate questions and politics at the scale of extinction. Pauling was born in 1901 in Portland, Oregon, and grew up in a world that did not feel designed to produce Nobel laureates. His father died when Linus was still a boy. Money was tight. The American West in the early 20th century was full of practical demands. But Pauling was the kind of child who could not leave a question alone. He was drawn to chemistry not because it was fashionable, but because it promised an explanation for why things are the way they are, why a material is hard or soft, why a liquid smells sharp, why a crystal forms angles as if it knows geometry. Chemistry had long been a science of substances and recipes. Mix this with that, heat, cool, isolate. But by the time Pauling came of age, chemistry was slowly turning into a science of structure. Atoms were no longer philosophical tokens. They were becoming concrete elements of a new architecture. Electrons, bonds, orbitals. These were the pieces, and the promise was that if you understood the arrangement, you could understand the behavior. Pauling's early training carried him into this transition. He studied at Oregon Agricultural College, later Oregon State University, and then went to Caltech for graduate work. Caltech in the 1920s was not just a campus, it was a furnace. American science was trying to catch up to Europe, and young researchers were being trained in a new style. Mathematics was no longer optional, and physics was no longer someone else's department. Pauling absorbed the idea that the boundary between disciplines is often just a habit of language. A crucial moment came when he traveled to Europe on a Guggenheim Fellowship. Quantum mechanics was erupting. The old models of bonding, like little hooks on atoms, were collapsing. In Germany and elsewhere, physicists were proposing that electrons behave like waves and probabilities, and that bonding is not a mechanical grip, but a stabilized quantum state. Pauling returned to the United States with a strange confidence. The new physics could be used not only to interpret chemistry, but to make chemistry feel inevitable. What Pauling did next was both audacious and intensely practical. He made the chemical bond the central object of explanation. It sounds simple now, because we teach the bond as a basic idea. But at the time, the bond was a messy concept. Chemists had rules and valences, but no unified theory for why atoms preferred certain partners and certain shapes. Pauling built that unity by combining quantum ideas with an engineer's hunger for usable rules. He introduced and refined the concept of hybridization, the idea that atomic orbitals can mix to form new orbitals that point in directions matching observed molecular shapes. This was not merely a trick. It was a way of saying, the atom is not a rigid set of boxes. It is a flexible probability structure, and when it enters a molecule, it reshapes itself to stabilize the whole. He also formalized electronegativity, a measure of how strongly an atom attracts electrons in a bond. Again, it sounds like a textbook definition, because his work helped make it one. But think of what it did. It turned chemical personality into a scale. It gave chemists a quantitative way to predict polarity, reactivity, and the distribution of charge. It took the vague feeling that oxygen is greedy for electrons and made it a number you could use. His masterpiece, in many ways, was The Nature of the Chemical Bond. It was not just a book. It was a declaration that chemistry could be explained from first principles without losing its richness. It argued that the world's solidity, its flexibility, its colors and smells and strengths all emerge from the ways electrons arrange themselves between nuclei. The bond was no longer a cartoon line. It was the central bridge between the quantum and the tangible. If that were all, Pauling would already be one of the giants. But his life carried another thread, one that leads into biology. The mid-20th century was a period when the boundary between chemistry and life began to dissolve. Proteins, enzymes, heredity, these were no longer mystical biological facts. They were structures, and structures could be understood. Pauling turned his attention to proteins with the same instinct he had brought to molecules. He asked, if proteins are chains of amino acids, how do those chains fold into stable shapes? not as an artistic flourish, but as a consequence of bonding. Hydrogen bonds became the key. They are weaker than covalent bonds, but when you have many of them, they can organize large structures with surprising strength. Pauling realized that if you arrange a polypeptide chain in the right pattern, hydrogen bonds can form regularly and hold the chain in a repeating shape. This led him to propose the alpha helix and the beta sheet, two of the fundamental motifs of protein structure. The alpha helix is a spiral staircase of a chain, stabilized by hydrogen bonds along its backbone. The beta sheet is a pleated arrangement, strands aligned side by side, again stabilized by a regular bond pattern. These ideas are now so foundational that it is hard to feel their original shock. Pauling was not merely describing proteins, he was showing that life's complexity rests on repeating physical constraints. Life was not magic, it was chemistry under pressure, chemistry given time. Then comes the episode's famous shadow, DNA. In the early race to understand heredity's physical basis, Pauling was one of the contenders. He proposed a model of DNA structure, one that turned out to be wrong. His model placed the phosphate groups inside the helix in a way that did not make chemical sense once carefully examined. Why did he miss it? Partly because science is not only intelligence, and information arrives unevenly. He did not have the best X-ray diffraction data. He did not have access to crucial images that would guide the geometry. And partly, perhaps, because his success had trained his instincts to trust elegance, even when the chemistry was protesting quietly. The correct structure, as the world now knows, would be a double helix, with base pairing and an external sugar phosphate backbone. Pauling missed it. But the miss matters not as a humiliation, it matters as evidence that even giants operate under constraints of access, timing, and human bias. Being brilliant does not mean you are immune to the speed of the race. Pauling's scientific life would have been enough for one lifetime. But Pauling had another dimension. He could not stop thinking about the moral implications of the nuclear age. World War II ended with a new kind of weapon. The bomb was not just a large explosion. It was a transformation of politics into a countdown. For a scientist who understood molecules and energies, the bomb represented the ultimate perversion of knowledge into leverage. Pauling became a public advocate for nuclear disarmament and against atmospheric nuclear testing. He worried about fallout, about radioactive isotopes entering the food chain, about genetic damage, about a slow poisoning that would be invisible until it was embedded in bodies. In the 1950s, this was not a safe position. The Cold War had turned dissent into suspicion. Scientists were expected to serve national strength, not challenge it. Pauling did not accept that bargain. He and his wife, Ava Helen Pauling, worked together in this activism. It is important to say her name. Ava Helen was not merely a supportive spouse. She was an intellectual and political partner who shaped the direction and courage of their public work. Their marriage became, among other things, a joint moral project. Pauling circulated petitions, wrote, spoke, argued in public, and collected signatures from scientists around the world. He was attacked for it. His passport was revoked for a time. He was called naive, dangerous, even disloyal. Yet he persisted with the same stubbornness that had once made him stare at bonding rules until they yielded a pattern. And then history did something rare. It rewarded a moral stance with formal honor. Pauling received the Nobel Prize in Chemistry in 1954 for his work on chemical bonding. Later, he received the Nobel Peace Prize in 1962 for his anti-nuclear activism. 2 Nobel Prizes. And not just 2 in the same domain, but in 2 radically different domains, one for explaining how matter holds together, and one for insisting that humanity should not use that knowledge to destroy itself. His life becomes a kind of parable. But we should be careful with parables. Pauling was not a saint. He was a human being with blind spots and controversial positions later in life, including ideas about health and vitamins that many scientists considered unsupported. Giants can be wrong. They can become attached to their own narratives. But the core arc remains. He stood at the boundary of chemistry and conscience. So how should we remember Linus Pauling? We should remember him as the man who made the bond intelligible. Not just as a line on paper, but as a quantum story with consequences. We should remember him as someone who saw that structure is destiny. The shape of a molecule determines its behavior, and the shape of a political world determines whether knowledge becomes medicine or weapon. We should remember him as someone who believed that scientific authority is not merely an honor, it is a responsibility. And responsibility sometimes means becoming unpopular. If you want a final image, picture Pauling at a chalkboard, drawing an orbital diagram, then stepping away from the board to speak about fallout, as if the same seriousness must apply to both. Because to him, it did. He did not separate the technical from the ethical. He treated them as one continuous problem. What we know? You have been listening to Scientific Giants Who Changed the World. Today, we followed Linus Pauling from the quantum logic of bonds to the spiral logic of proteins. From the ambition to understand life structure to the moral courage to confront the nuclear age. In our next episode, we will meet Rosalind Franklin, whose work in a dim laboratory helped reveal the structure of DNA, and whose story forces us to confront how credit, power, and gender shaped the history of discovery. Until then, thank you for your attention and your time. This episode was written as a continuous story for the ear, because a life like Pauling's cannot be reduced to a list of achievements. It has to be walked through step by step until you feel how knowledge becomes both explanation and obligation.